We discuss now what we call as Stokes problems, impulsive motion of an infinite plate. The motion of the fluid is set into motion when the plate is set into motion with impulsively. So this was first considered by Stokes. Stokes has worked in many aspects of problems of fluid flow, mathematics, vector analysis, applied mathematics, etc., etc. And there are large number of problems in which he made very important considerations, and many of those problems are known as Stokes. All of them are known as Stokes problem. One of the very famous problem, for example, is the one in which the fluid is very viscous, and therefore the motion that is generated is very slow, and it's known as creeping motion. That type of motion is also known as Stokes problem, and we will be discussing that at some stage. But this problem, which we define by setting impulsive motion of an infinite plate, is also known as Stokes problem. We consider an infinite plate and impose the following conditions on the fluid flow. Rayleigh also, by the way, it may be mentioned that Rayleigh also considered the same problem. So you can see that u is 0, the velocity component u in the x direction is 0 for all y when t is 0. That is, initially u is 0 for all values of y. U is 0 for all values of t as y tends to infinity. So as the value of y increases to infinity, that is, we take the distance away from the plate, then u is again takes the value 0, even if the t is greater than 0 for all times. And then it says we set u to be equal to some constant velocity whose value is reflected here as capital U infinity at y is equal to 0 for all time t is equal to 0. So when y is 0, the value of u is set as u equal to capital U equal to infinity. The conditions A and B, they help us to define another variable, and the two conditions can be combined into one. So instead of writing two different conditions, we can write one, and therefore these three conditions will be reduced to 2. And we define a variable eta such that eta is equal to y over 2 nu t under root. And by combining the two conditions into one, we keep eta to be equal to infinity. Making these transformations, we can write down the equation u is equal to u infinity into some function f of eta. And from the Navier-Stokes equation, we get the equation to be equal to f double dash. That is, this is equal to d2f by d eta 2 plus 2 eta into df by d eta equal to 0. The boundary conditions are eta is 0 when f is equal to 1, and eta is infinity when f is equal to 0. So what you see is the three boundary conditions earlier has now been reduced to two boundary conditions. So three boundary conditions have been reduced to two. It has simplified our problem. This is a standard equation, and its result is we obtain as u of yt equal to u infinity, which is some constant, times complement of air function described in eta. So where complement of air function is equal to 1 minus air function. So this is a standard notation. And the air function itself occurs in mathematics, and this is defined as this value as shown here, integral from 0 to eta e to the power minus alpha square d alpha. And from here we see the vorticity that diffuses from the plate into the fluid as this. And what does this reflect? The same type of conclusion earlier. As the y increases, the value of w decreases. And when t increases, then this whole function increases. Anyway, the fluid is controlled by the boundary conditions that we have imposed on the variable eta. The wall shear tau w, that is tau, the shear force at the wall w, is given by the standard thing du by dy, and at the wall y is equal to 0. So this will be the value of tau w. It turns out to be equal to this, which resultantly is equal to this. And then the distance through which the effect of viscosity penetrates due to the motion of the plate is a function of time, and it is defined as this equation delta. And we can see that delta is of the order of t to the power half. That delta changes, it varies as time, root time. So that means I meant to say this. And it increases with time. If t increases, the delta increases. If t reduces, this reduces. So these are the important solution aspects of impulsive motion of an infinite plate, or in other words, one of the Stokes problems that he discussed.